Okay. Now, when you have a problem that's Hess's law, adding and subtracting of equations, typically you're given a target reaction. In this case, carbon plus O2 gas goes to CO2 gas. And delta H of the net, I just put net down here, is our objective in this. You're given two reactions, and if you look all the way to the bottom, number 10 down there, you're given three reactions, and I've seen problems with having 4 or 5 reactions where you have to work together, and we'll talk about that. Okay, you're given the first two reactions. I call reaction 1 is the carbon solid plus 1/2 O2 gas. I need some more room here. I better move this back a little bit. There we go. And this shows carbon monoxide, and we'll hold this delta H1 and simplify the notation a little bit. It's all standard state if you need to put that in there. Okay, and of course reaction 2 that's given is the carbon monoxide plus 1/2 O2 gas goes to the CO2 gas, and delta H2 is equal to a minus 283.0 kilojoules, like this. Now, the object is to add those two together so that you get the target reaction. So, we'll put a little line under here like we're adding math problems, just like this. And so when we look at adding these two together, what we do is we can do certain things to these reactions. You can increase them by multiples, you can cut them into fractions by multiplying through by fractions, or you can reverse the reactions. Okay, and we'll do all of this as we go along. What you need to do is look at your target reaction and then study how the arrangement of the givens are. Is one of the givens have a product of CO2? Yes. Is the givens got reactants of carbon? Yes. Oxygen? Yes. Like that. And then you manipulate these multiples or fractions or reversing. If you reverse, you have to change the signage. Now, we'll do these, and I'll repeat these rules as we go through this. Now, in this particular one, nothing needs to be done. If you add these together, notice that there's a CO gas on the right and the CO gas on the left of the arrows. Okay? And that eliminates the carbon monoxide in the net equation when we add it together. So we bring down the carbon solid. Half is an O2, and that's a gas, believe it or not, right there. And that goes to CO2, which matches the target reaction. So we've achieved that. Now, the reaction here for the net reaction is the sum of the algebraic sum, I should say, of those two numbers. So the delta H net is equal to the delta H1 plus delta H2 under standard conditions, shown here. So of course that would be equal to a minus 110.5 kilojoules plus a minus 283 kilojoules and that comes out a minus 393.5 kilojoules, as shown in the answer. And so the net energy change for the net reaction is the sum of those two, as well as the sum of the energy numbers. So that's number one in there. So that is an introduction to adding equations using Hess's law. So in number two, you're given target reaction. Now I embellish my notes during the lecture for your benefit, but you don't have to draw all that target reaction stuff. And so we're given phosphorus trichloride plus Cl2 going to phosphorus pentachloride, and obviously we're looking for the net energy change. Now, given reaction 1 is 2 phosphoruses plus 3 chlorines going to 2 phosphorus trichlorides, and the overall for that one is equal to minus 640 right there. And we're given also for reaction 2 phosphorus plus 5 chlorines goes to 2 PCl5s, and delta H2 is equal to a minus 886 kilojoules. So we need the net reaction for the target reaction. So looking at the givens and looking at the target reaction, I tell people to keep one eye on your reactions given and one eye on the target reaction, and manipulate to achieve the target reaction. So when you look at these reactions against this right here, we see a PCl5 is on that side. Well, that's fine. Okay, so right now we don't do anything to the second one. And then we look at, well, I need a PCl3 on the left. Well, here's the PCl3 on the right in this first reaction. So what we'd have to do is reverse that first reaction. And what I tell people to do to keep their bookkeeping straight is rewrite everything but include the adjustments. So since we need to reverse this, that's what we will do. So reaction 1 now becomes 2 PCl3. See how I reversed it? And that goes to 2 phosphorus plus 3 Cl2s, and when I reverse it, delta H1 becomes endothermic now. So I'll put the plus in for emphasis, just to emphasize that. So no multiples have yet been applied. Now, the second reaction, we do not need to make any changes here. So I will rewrite reaction 2 phosphorus plus 5 Cl2s go to the 2 PCl5s as we have shown, and delta H2 is equal to still 886 kilojoules. Okay, like that. Now, again, I'll put a line under the reactions I'm trying to react, and we look at this one has 2 phosphoruses on the left, 2 phosphoruses on the right, and then we will add what we have together in this context. So we have reaction net is 2 PCl3s plus 5 Cl2s. Oh, wait a minute. sorry, here we have 3 Cl2s, I forgot that, and so this reduces to 2 PCl, sorry about that, 2. Everybody okay on that? All right, stop me if you need to, please. And that goes to, well, no change on that one, PCl5, and what we have is the net reaction will be delta H1 plus delta H2, but I stop right there just for emphasis. However, when you look at what we have here, look at the net reaction and look at your target reaction here. Okay, what do you see? Everybody has a coefficient of 2. Well, you can divide that reaction by 2 all the way, but all the way through. That is, you have to divide both sides of the reaction, is what they say in math. You can do anything to an equation as long as you do it to both sides, right? So I'm going to come down here with one more equation just to emphasize this. People get good enough at this, they just eyeball it and write the net reactions like that. Now, if you divide the equation, obviously you have to cut the net in half. And so that would be, of course, 1/2 of the delta H1 plus delta H2 algebraically added together in this. So this gives us a reaction net. Now, yes, you have to go through all these little details in order to solve one of these. So that gives us the net reaction of PCl3 plus Cl2 going to PCl5, which matches our target reaction. And so the delta H net now is 1/2 of these two. So don't get confused right here, because when you make the changes of direction on the reaction or reverse the reaction, you have to use the reverse energy values. So that would be a plus 640 plus, trying to get all the embellishments in here, 640 plus a minus 886, and of course that's all in kilojoules, and that net comes out to a minus 123 kilojoules for that net reaction. So they're quite involved, but with a little patience and trial and error, you can get through these without any errors. More of the same, keeping the on the target reaction. We want to manipulate these two in order to add the two energy values together and get the net energy change for that particular reaction. This is ethanol and going to dimethyl ether. Anyway, we start out by looking at the given reactions and seeing if we need to make any changes. So we see that ethanol is on the left for the first reaction, but when we look at the second reaction, obviously the dimethyl ether is on the product side. So this one will have to be reversed. And again, we rewrite the reactions. Yes. Now, the second reaction we will reverse. And so it would be, the new reaction 2 would be 2CO2 plus 3H2O would go to dimethyl ether plus 3O2, and we will change the signage in delta H2 to a plus 1328.3 kilojoules. Okay, so have we arrived at close to our target? Well, we have 1 mole of C2H5, 3 moles of O2. That looks pretty good. That'll cancel out with the other side. Let's see how we can do that. Here, and here, here, and here will cancel out. And so we have 3 waters also canceling like this. And the target reaction is the one in that reaction here. Of course, that's the reversed, includes the reversed reaction. So then this is a minus 1234.7 plus 1328.3. It's all in kilojoules. And we see an endothermic reaction, 93.6 kilojoules for that reaction, like that. Now, just to re-emphasize some of the notations here, again, you can either detach it from the reaction, just to emphasize these notations again. That a little bit. Or you can include it in the equation. So just giving you some notation review there, and so let's see. Okay, so number 5, our target reaction is 2F2 plus 2 H2Os goes to 4 HFs. Is what our target reaction is. Now we're given H two given is water reaction. So, looking at our target reaction, HF's already on the right here. However, in the target reaction, we see 4 HFs against 2 HFs. So what we'll have to do is multiply through to increase the number of HFs. Now, sometimes this gets real tricky, and you have to play with the combinations of reactions. But regardless of how many reactions, always work in pairs of reactions in these kinds of problems. I don't know where you're going in the future, but the idea is to work in pairs and work them down to a net pair and then add to the target reaction. Well, anyway, so reaction 1 has to be multiplied by 2. As long as you can multiply both sides, we go to 2H2 plus 2F2 goes to 4HF. Now, you must multiply the H1 given by 2 also. Multiply 2 over here if you want to. 2 times minus 5, 4.2 kilojoules, like that. And that's going to give us a minus 1084.4 kilojoules. Okay, so that's our first reaction, and again we had to multiply through by 2 on everything in order to get the 4 HFs. Now the second reaction, we see H2O on the left, but here in the second reaction is on the right, so we have to reverse the second reaction. So it goes to 2H2O 2 plus O2 and delta H2 is equal to 571.6 kilojoules. And when we reverse it, we have to change the signage to a plus. So then we add these together, see if we get the net reaction. Okay, so we have 2 F2s right there, and we have 2 H2Os right there. 2 H2s will cancel, and that will go to 4HF, and 1O2, and delta H net is now our new delta H1 plus delta H2, like that, and so that would give us minus 1.4 plus 571.6, and that all comes out in kilojoules. Yeah, and this ultimately is 512.8 kilojoules, and if you included it in the reaction, it of course would be entered on the reactant side. Okay, now the point I made earlier in working multiple reaction type problems like this is to always work in pairs of reaction, combine 2 and then work with the last reaction and then combine it, but only work in pairs. You can't really manipulate all 3 at the same time and then add together. Now, long story short, if you look at the arrangement that we have here, what you're going to find out is we're going to have to multiply this one by 4. And the second one we'll have to multiply by 2. And we're going to have to reverse the last reaction. So we'll start with these two. I am shortcutting, so bear with me. Okay, so the first one, multiplying by 4, gives, move it over a little bit, reaction 1 now becomes 4 carbons plus 4 O2s plus 4 CO2s, and the energy value, number 1 now becomes 4 times a minus 393.0 kilojoules, and that is 1574 negative kilojoules for reaction 1. Now, reaction 2, we multiply through that one by 2, and we have 2H2 plus O2 goes to 2H2O, and delta H2 is equal to a minus 2 times a minus 5.8 kilojoules, which is 571.6 negative kilojoules on that. Okay, so now we want to add these two together, get a net reaction 1, 2, and then add that one to reaction 3. So that's the essence of what I'm talking about. Okay, so we wind up with reaction 1, 2, like this, and it comes out 4 carbons plus 2 H2s plus 5 O2s goes to 4 CO2s and 2 H2Os, and delta H1, 2 now becomes the sum of those two, and I'm just going to give you the net here. When these two are added, gives a minus 2,145.6 kilojoules right there. So that kind of speeds things along for us. And that one. Now we enter in the last reaction, but we have to reverse it. Remember what I say up here? So we'll reverse reaction 3, and you can, some people will go in here and use primes for any manipulations that they do to distinguish between the first ones. I don't. It doesn't matter one way or the other. Anyway, this one would be 4 CO2 plus 2 H2Os, give you 2 C2H2 plus 5 O2s. And the delta H3, of course, is listed. You'd have to reverse or change the signage to 598.8 kilojoules. So we go through and start canceling terms. Now, this is not as simple as I'm making it sound. So a lot of times you have to backtrack several places in multiple reaction systems like this. That's why I limit the exam review to just 2 reactions. So the outcome of this can be 4 carbons plus the 2H2 goes to C2H2, 2, and the delta H net, delta H1 and 2 plus delta H3. So that gives us a minus 2145.6 plus 2598.8, all in kilojoules. And that concludes to be plus 453.2 kilojoules. Now, this gives a 422. That's not standard. What is a standard equation? The lowest whole number ratio, right? Isn't that the case? Okay, so we need to adjust to standard. So essentially, the final answer would be dividing through by 2, and we'd have 2 carbons. I'm trying to keep it all on the page. H2, which would go to C2H2, and delta H net would be half of the 453.2 kilojoules, and that equals 226.6. Anyway. Now, the Hess law equation is a shortcut in calculating the net energy of reaction using what we call standard heats of formation. Now, we mentioned these back at the beginning of the course when we were writing the types of molecular equations. The molecular equations contain formulas which are in what we call basic standard states for the substances. So, when we write Hess's law for any reaction, and again it's the sum of the moles of the heats of formation of the products minus the sum moles times the heats of formation of the reactants. And this, well, delta HF is defined as the standard heat formation. This is the most common form of substance that it exists in. At the back of your textbooks, in the Appendix C in the Ebbings text, you'll see thermodynamic quantities for substances and ions at 25 degrees Celsius. The standard for thermodynamics is 25 degrees Celsius in 1 atmosphere, and I'll develop that if you take Chem 2 and you get to thermodynamics. Anyway, you have 3 columns in each of the substances, delta HF, delta FGF, and S. S is the entropy, a measure of disorder, and that's another story. Delta G is called free energy reaction. That's the work capacity of the substance. But this is the one we're interested in right here, the delta HF. These are heats of formation of the substance in their basic standard state, or their most common state. Elements are always 0 in basic standard state. So if you look at aluminum, come down here to barium, and come on down to, well, beryllium. You can see here, they're all zeros. But compounds, you don't have many variations in compounds like you do elements. Like bromine will have different forms, but only one Br2 liquid is its basic standard state. But substances like water, it only has 2 really forms, and that's steam and liquid form, well, ice, but they don't have an ice in here. But they delta H, H2O for water. Okay, when we look up water, you've got water and gas phase and water and liquid phase, and you have a delta HF for each one. So, but water is water, and so depending on what the equation is asking for is the number you would use over here. Okay. Okay, this is how we proceed on this. Now you'll be given an equation and asked to determine the heat of reaction like this. So you're given, say, C8 methane in the gas phase plus 2 O2 gas goes to CO2 gas plus 2H2O. We'll make that liquid form in this one, and delta H of reaction is the objective of the problem. Okay, so we start these problems by writing down the equation in, say, a horizontal like this, and then over here on the left, make your symbol delta HF right here. And what we'll do is we'll look up the values in the tables for each one. Now the problems, will have them listed below the problem. But if you don't have the listing, then you go find methane in the textbook, and it's a minus 74.87 kilojoules per mole. Now the equation is showing 1 mole. So shorten this thing up. I usually just put the moles like that and just put kilojoules and then put a bar between the elements and the substances like that. So each one of these will have a little listing under it like that. Well, then this 1 times that number is a minus 74.87 kilojoules. See, that's kilojoules per mole times moles. Moles will cancel out. Okay. Now, O2, if you look it up in the table, has a 0 kilojoules per mole. I don't even put anything but 0 there. Okay. Now, CO2 does have a value. CO2 is listed as a minus 393.5, and we have 1 mole of that. And that's kilojoules, of course, and minus 393.5 kilojoules. Then water has 2 moles attached to it, so whatever we find, we must multiply by 2, and liquid water is a minus 285.8 kilojoules, and that's 570.6 exo in that. Okay, so that's the first step in this kind of problem. Now, what I recommend to students once you first start this is isolate the products and reactants, like I'm showing you here, because when you apply these numbers to this, that's what you're going to the Hess law equation. That's what you're going to do. You're going to algebraically add the product numbers, and then you're going to algebraically add the reactant numbers and take the difference between the two. And so it's set up like this. So your delta H of reaction now is equal to products minus reactants. So what I suggest is isolate each one. And it's all going to come out in kilojoules, so I usually drop the units and just manipulate the numbers and then tag it with kilojoules on the end. So you're going to add these two, so that's 393.5 plus a minus 570.6, and all that's in kilojoules. So there's your product values here. And you want to subtract the reactants. So the reactants are minus 74.8 kilojoules, 87 kilojoules, plus, of course, the 0, just to emphasize the summation, and those are in kilojoules also. So simplifying, removing and distributing the signage, 393.5 minus 570.6 plus, see, minus times a minus, 74.87, and of course 0, and everything comes out in kilojoules. I get a minus 889.3 net for the reaction given. So it's a lot simpler if you set it up and in little table forms like I'm showing you here, so you can keep up with your bookkeeping, so to speak, and your signage doesn't get tangled up. That's the one area that students typically get confused in, or drop a sign, or forget the minus times a minus, or something of that nature. Physical transitions like evaporation, condensation, freezing, all have heats of formation also in different phases. So you have the same substance, but the state of existence is different. So when we look up water in the liquid phase, we have 1 mole times a minus 285.8 kilojoules, and we have 1 mole in the gas phase, 241.8 kilojoules, like that. So this is what you're looking for, and so delta H of that reaction, or simply the boiling of water, requires for per mole is the products minus the reactants. Well, 1 times that will give you, of course, a minus 241.8 kilojoules minus a minus 1 times that number, 285.8 kilojoules, and overall it comes out a plus 44 kilojoules net reaction. So you can come up here and go delta H of reaction is a plus, if you want to put the plus in, 44 kilojoules. That is a very classic reaction that's used many times in explaining certain phase transitions for water, like that. But I just want to work one through just kind of from inspection. So much simpler, obviously, than the Hess law addition and subtraction of equations. Okay, so what we're looking at here is what we call a bomb calorimeter problem. And it's very simple, very straightforward, but I do need to emphasize a couple of points about this, okay? Suppose we're given 0.562 grams of graphite, which is standard form of carbon. Like that. And it's placed in a bomb calorimeter at temperature 1 is 25 degrees. And let's see. Okay, here's the calorimeter constant. Typically is given by the manufacturer, and it's called C sub V, which is the specific heat is what is called at a constant volume, because so you can't, the bomb calorimeter doesn't expand or compress, and it is 20.7 kilojoules per degrees Celsius. So the reaction temperature change in temps goes from 25 degrees Celsius measured to 25.89 degrees Celsius, and of course this gives us a delta T equal 25.89 minus 25.00 degrees C. .89 degrees C change in this. Well, I gave you the calorimeter equation. Yeah, you got to memorize it. Okay, so Q for the calorimeter is C sub V delta T. Not very difficult. And so what this gives us is the calorimeter constant times the change in temperature, 20.7 kilojoules per degree Celsius, times 0.89 degrees Celsius, pretty straight. That cancels and cancels, and so we're left with 18.423 kilojoules is the energy transferred into the water. Okay, that's the amount of energy. Now, this is the energy from 0.562 grams of the graphite. This is the issue, and you need to express this in kilojoules per mole. So if this is the kilojoules per 0.562, and we're going to change it to molar amounts, that would be 18.423 kilojoules per 0.562 grams. Now, how do you convert grams to moles? Divide by formula weight, obviously. So we want to divide by 12 grams per mole, and then simplify that. It comes out in kilojoules per mole. So that's and I get 393.37 kilojoules per mole. Let me get that out of the way. Exothermic. How do I know it's exothermic? Well, when you do a bomb calorimeter, the energy is delivered from the reaction chamber. I showed you the picture earlier, to the water, and you're measuring in the surroundings. So the increase in energy means it had to come from somewhere, and that was the reaction. So the reaction energy is what is defined. So now if you wrote it into an equation, you would put the negative into the reaction. Carbon, graphite, plus O2 gives us whatever products, and delta H of reaction is equal to a minus 393.37 kilojoules per mole carbon, graphite, like that. So this sometimes confuses people in the given when the data comes to them. They're not going to tell you it's a calorimeter. They'll say the specific heat of the calorimeter is such and such and such and such. And when you see specific heat defined here, in kilojoules per degree Celsius, it's the amount of heat necessary to raise 1 mole of substance 1 degree Celsius. And that's what the calorimeter constant is. So you won't be confused, hopefully, if you see that problem. And the main thing is that you convert the grams to moles and divide into whatever the CV times delta T is. Okay. On this one, we're talking about the first law of thermodynamics. Let me do it this way. I'm sorry. Let's just talk about laws of thermodynamics. First of all, thermodynamics is kind of self-defining. It's the study of energy changes in physical and chemical process. Now, anytime a chemical reaction takes place, two events have to occur. A reaction must experience, one, a change in energy, and two, a change in state of order. Now, you can have a change in energy, but if you don't define the change in state of order, you really haven't defined the reaction process to its completion. That is, there are salts that you can dissolve in water, for example, and one will get, the beaker will be cold, and you dissolve a different salt in water, and the beaker will get hot, but both of them show clear liquids. You can't tell what one against the other, so you have to include, well, they dissolved and dispersed, and so their order has changed. And so that's what I'm saying, that you have to change the energy, you have to change the state of order, dispersion. It has to go to a more disordered state. That is a ball rolling down a hill. The reaction doesn't proceed unless you turn the ball loose, and it rolls downhill. It goes to a lower energy level and a lower state of, in a different state of order, from high order to low degree of order. So in essence, that's what thermodynamics is all about. And I'm simplifying it extensively. In the process of studying the reactions, the change in energy revolves or involves what we call the first law of Thermo. And the state of order changes is simply the mathematics and concepts revolving the second law of Thermo. When we talk about the first law of thermodynamics, then everything kind of focuses and funnels into heat of reaction and the capacity of that reaction to do work. And when we talk about all the math and the complexities of the second law of thermodynamics, it involves measurement of how disordered a process becomes or less disordered. Now that's a story that evolves in Chem 2 in the formal chapter on thermodynamics. But what we're studying right now is actually the change in energy that associates only with the first law of thermodynamics. That's where all the Q expressions come from, and the calorimeter equations and the MC delta T's and all this evolve out of the first law of thermodynamics and the heats of reaction, enthalpy, and what have you. Okay. And that's the first law of thermodynamics. And this is dealing with the change in energy of reactions. And there are actually three changes that that occur. One is exothermic, another is endothermic, and the third is isothermic. And a process may go through many steps, but the starting energy winds up at the ending energy is the same place as the starting energy, and it means that delta overall net is equal to 0. Here, the delta H net, as we've shown you, is less than 0, comes out negative in the calculations that we've looked at. And the delta H net, of course, is positive in that consideration. So these are just simply definitions of what those terms are relative to the reaction process. Now again, exo, endo, and iso refer to what the reaction is doing, not the surroundings. However, it might be instructive to mention you can't measure the reaction. You always measure the effect of the reaction on the surroundings. There's no way to stick a thermometer in a reaction, but you can put a thermometer in a solution in which the reaction is taking place and delivering energy into that environment, the solvent system. So that's what I'm trying to emphasize here in separating the system surroundings, that all our terminology is in terms of the reaction process. Okay. Now, when an energy change takes place in thermodynamics, we have two systems: open systems and closed systems. The open system is a reaction in which expansion and compression is allowed. And I'll demonstrate these in a minute. Or simply expansion and compression occurs. In a closed system, these are reactions and studies in which there is no change in volume. Let me just simplify it that way. No expansion is or occurs. Okay. In thermodynamics, the change in energy of any reaction is referred to as a change in internal energy. Which is energy due to its state of existence and its chemistry or chemical structure. So when we talk about the delta E of reaction, as in thermodynamics open systems, we're talking about a change in internal energy, which is energy final, minus energy initial. That makes sense, right? And depending on the outcome of this, we have endo and exothermics, depending on how the numbers come out. If it comes out positive, is endo, and negative exo. So that's where it is. However, this process involves two events. Again, the order and energy, but within the energy, it also has two events. And this is change of heat, delta H, the heat change, plus a change in its ability to do work, is what it's referred to, work. It has a work function. And this work function is dependent on expansion or compression. It's not either expansion or compression. And I'm going to explain in this. Now, the heat change is what we've just covered. The Hess's law, the proportionalities. This is listed in the delta E internal energy as equal to delta H of the reaction that we've just covered. All of those calculations we've been doing and the calorimetry we did in the first class on Thermo, that's this calculation. It is separate from the second part called the work function. Okay? And plus the work in thermodynamics, and I'm not going to go through the derivation of this, just go with me on this, is pressure, the atmospheric pressure, times the change in volume experienced by the reaction process. And in short, delta EI equals delta H of reaction plus P delta V. That's what it is. Now, that doesn't make any sense to you, I know, right now, but as I go through this, you'll understand it. Okay. Here is a reaction that's in an open system context. If we take, this is given 3H2 as a gas plus N2 as a gas goes to 2NH3 as a gas. Okay, all of the reactions, if you were asked a question, will start with, they'll give you a reaction, it'll have different states of existence, and it's the state of existence changes that are important here. Now, if you look at this reaction, how many molar volumes do we have here? It's 3 in hydrogen and 2 in nitrogen, but the total is 4 molar volumes. So it's 4 times whatever a molar volume is. On the product side over here, we have only 2 molar volumes. Okay? So as the reaction proceeds from reactants to products, do you see a change in molar volumes? Yes, you do. And you can count these if you've given out the reaction. You look at the gases and reactants, product side. Now, if it's all liquids on one side or solids, that molar volume is 0. Sometimes a solid expands into a gas. KClO3, for example, goes to this. KCl, both of these are solids, plus O2 gas, 3, 2, and 2. Well, this is a Vm is equal to 0 over here, and solid doesn't count, but you have 3 Vms over here of Vm equals 3. So you have an expansion here from 0 to 3 molar volume. Here is a compression reaction going from 4 to 2. Now you can count that. All of the complexities I've just defined just kind of puts where all this comes from in the thermodynamic world. But you look at a reaction, if the molar volumes on the left are bigger than the molar volumes on the right, it's simply a compression reaction. It's like squeezing a balloon. Or if it expands to a higher molar volume number, it's expansion of the balloon. You remove the walls of the balloon and all the gas flies out like that. Now, how does this apply to this equation up here? Well, here's your delta H. That's Hess's law and all that stuff, so you just calculate that. Here is delta H. We've seen this one, minus 91.8 kilojoules. That is that number. So you plug that 91.8 right there. But how do you get a number for this right here? Well, I've worked out standard pressure, 1 atmosphere against what we call changes in volume that lead to energy numbers. And so this now becomes delta H of reaction plus whatever the 2.5 delta V of molar volumes is. Now, this has a complication to it in that you have to apply signage to that term at the end of the calculation. So we'll go through both of these and show you what the point is here. Let me get a fresh page here. So what you're going to do is calculate the change in internal energy for the 3H2 gas plus N2 gas goes to 2NH3 gas, and you're simply given the delta H of the reaction is a minus 91.8 kilojoules. Okay, we're going to calculate that. Now, the first law equation is delta H of delta E internal energy is delta H of reaction plus 2.5 delta V. Now put a bracket around that because you're going to have to put a sign inside of that. Plus or minus is what I'm trying to tell you. And it's not hard to do, but you got to visualize it in your mind. The delta H is given over here. So we'll put that right here, minus 91.8 kilojoules. But how do I get the delta V? Well, I just showed you. Well, we have 4 on the left and 2 on the right, so your change, and you don't, it's just, the signage in this only defines compression and expansion. The final volume is less than the initial volume. Okay, so that gives you a negative delta V. But all that says is the delta V is 2 molar volume. So all you can do here is 2.5 times 2 right now. But inside that, you're going to put a sign right there, plus or minus, depending on what's happening. Now, here's how you do that. If you take a balloon that's, say, VM1, and this is a compression reaction from 4 VM to 2 VM. That's like, watch me, squeezing the gas down to a smaller volume. What are the particles going to do on your hand? They're going to push back on it, yes? Can you visualize that? This is the key to understanding this. So you're going from a large molar volume to a smaller molar volume. What are the particles doing? They're gaining energy. The particles are gaining energy and pushing back on your hand. So gain of energy is endothermic. So for that reaction, you have to put a plus in there. And then work this out. Because you're going from a V1 to a smaller VM2, and that is compression, and work energy is endothermic. Now, I didn't talk about the delta H here. I'm just talking about expansion work and compression work. If it's an expansion work in the first law, Q plus W, you have to assign to the work function a plus. Work energy is greater than 0. Now, you can work, this comes out in kilojoules also, so it's a minus 91.8 plus 5.0 in kilojoules, and whatever that comes out to be, 86 something, I guess. Yeah, 86.8 minus 86.8 kilojoules. Now, that's a small number. That's why, for the most part, people just put delta H's in books, because this is not going to make a big difference. But it is real in terms of the thermodynamic analysis. Now, looking at the second equation I want to show you, and that is the, well, we were using 2KClO3 as a solid, going to 2KCl solid plus 3O2 gas, and we need the delta H net for that one. What is that? Well, let's go to the back of the book and calculate it. We'll do Hess's law and show you how the bigger picture is. Okay, so we need this one first, and then we'll go back and get the work calculation, because we can get work right now. So molar volumes in the reactant side is 0. Well, the molar volumes on the product side is 3. So your change in molar volume is 3 minus 0, which is equal to a plus 3, and that says you have an expansion reaction. And this gives you your work. All right, so you remove the walls of the balloon, mentally remove the walls, and the particles move further apart, and they relax. That's the way I think about it. So if they're relaxing, what's happening to their energy? Yes, exo. So that's why you assign a negative to an expansion to work. for an expansion reaction. And so this would translate to delta EI to equal delta H plus P delta V, that's the heat of reaction, and we haven't figured that yet, plus 2.5 times 3, and inside here we'd have to put a negative, and then calculate your delta H using Hess's law of this. Let's see if we've got it. KClO3 goes to KCl plus, I'm going to, yeah, well, O2, 3, 2, and 2. So let's look up delta H of formations for these and calculate Hess's law numbers. Let's see if I can. So now we have that, and so delta H of our reaction is products minus reactants, so I'd have 2 times a minus 436.7 minus 2 times a minus 397.7. See, I'm applying now what we've already used. And so that would give us, so we apply Hess's law, and I got a minus 78 kilojoules. You might back me up on that, just in case I missed a button. But that number now goes here. And so you've got the first count part of the delta H, and then your second part of your internal energy calculation. So now we come down here and make the substitutions. Delta EI is equal to minus 78 plus a minus 2.5 times 3, like that. And everything's going to come out in kilojoules. And that's also a negative plus 78, and I get a minus net 85.5 kilojoules net. There. So once I get that 85.5 net there, now I can go ahead and finish my internal energy. No, that is the internal energy, sorry. Net internal change in internal energy. Right there. Okay, now that seems like a lot, but it's really not in terms of making the calculation, because the delta I've given you the foundations for delta H of reaction and what expansion compression work functions are. Now there's one complication that engineers run into from my classes than the pure scientists. In pure science, let me show you this. The process. Can you all see that? It says here, the change in internal energy, which I've just shown you, is delta H plus P delta V. Just shown you that. Is the same as delta E equals delta H minus P delta V. That's a real what? Well, here in this equation, you must specify compression and expansion and make an assignment of sign in the work function. Exo or compression, endo. Over here, you do not. In the work function, you do not. Just calculate change in molar volumes and substitute. All right, and I'll show you how this works. Over here, we had 3H2 plus all gases. N2 goes to 2NH3. Your change in molar volume was 2, and we had to apply, it was a compression. So your change in molar volumes decreased, and so this is a compression, and so your work is endothermic. And so when you calculate your delta EI, you have to put that endothermic plus into delta H plus a plus work, like that. You made that assignment. Over here, you don't have to do that. For the reaction, 3H2 plus N2 goes to 2NH3, your delta Vm is equal to 2 minus 4, negative 2. So plug that into that expression. Delta EI equals delta H minus P times a minus 2. Minus times a minus is a plus, and therefore delta EI is equal to delta H plus whatever that P delta V is. And so you have the same expressions that it winds up. Now, typically this shows up in engineering text, and you have to just simply look at the products minus reaction, plug in the change in volume. But your text and most chemistry college texts will give you the term here. Now, only one more thing I need to say here about this, and that's your closed system. Well, everything I've done up to this point is a closed system, except this that I've just presented, open system. Why? Closed systems, let me show you what a closed system is and we're through. There are three closed systems. One is when the sum of the change in molar volumes of the reactants equal the sum of the change in molar volumes of the products. For example, if I have I2 as a gas plus H2 as a gas going to 2 HI as a gas, we have Vm is equal to 2, and over here I have Vm equal to 2. So when I apply this to the first law equation, I have delta EI equals delta H plus P delta V, and delta V here is equal to 0. So when I plug that in, delta EI equals delta H of the reaction. And that delta V equals 0 is a closed system. The second closed system is your bomb calorimeter. And I've already shown you that because delta V equals 0 for that bomb calorimeter. So you have this chamber, delta V equals 0. And so there's no change in that chamber. It doesn't expand or compress. So delta EI for this one equals delta H of reaction, and that's equal to C sub V delta T. That's the bomb calorimeter problem. So that's all that involves. The third one is solution phase reactions. Here you're talking about, say, an acid solution and a base solution being mixed into, say, a calorimeter. Some people call it a coffee cup calorimeter. They take it, and you get a volume, which is acid plus base mixed together. However, it's when they mix, at the instant they mix, before the reaction takes place, you have volume 1. Then the reaction takes place and sends energy into the water, which you measure using a thermometer or a thermocouple. But V1 and V2 are equal because the water in a moderate change in temperature doesn't explode out of the beaker. It doesn't change, the temperature change in the reaction doesn't change the volume of solution. Water doesn't expand like a gas does. So when you calculate the energy transferred into the water, you use the MC delta T. And delta V equals 0. And all this is giving you is delta H of the reaction in solution. The work is 0 because there's no expansion in the liquid. So your 3 forms of the closed system we've already done. In the last lecture we did all the calorimetry and showed you the heating curve of the water. That's a closed system. I just did a calorimetry problem today, okay? And it's not a real big deal calculating volume on the left, volume on the right. If they come out 0, it's closed system. And so whatever the delta H is, that's all you've got for your internal energy. And so I wanted to bring this in last. I always do that because you've already had the experience with the calorimetry. And this is a lot of material.